Well, hi. Thanks very much for inviting me. It's really an honor to be here. And by the way, my wife is in Brussels with me, and we just love Brussels. It's just really great to be here. Now, nobody's wildly waving their hands, so I assume that you can all hear me, right? Okay? Okay. Again, I know that there's a huge amount of work that goes into producing a conference like this, and it's just really appreciated. I have to start out with a commercial. Looks like we've lost our... Yeah, I think I accidentally hit. Okay. I don't see it here. All right. Okay. Good. So I do have to start out with a commercial. I have a book coming out at the end of the month. This book, if you're sitting kind of close or even not so close, you can see I have some gray hairs. Before I had gray hair, I actually wanted to do this book project. So it's really like 30 years in the making. I hope you take a look. Okay, so much for that. Now, what am I really going to do here? The problem is, actually Joe Rickard and I were just talking about this earlier. People really get attached to certain software and certain software concepts, and so everybody's got an opinion. I have mine, and I'm going to present mine. I don't mean to say that what I'm going to present is 100% the must way to do it, and I definitely hope to see a dissenting opinion. But basically what I'm going to do is in the computer science world, and by the way, I originally come from statistics, so that's why you see a regression book there, and I do statistics, even though I'm in a computer science department. Now, in computer science, you have something called design patterns, which is sort of a general way. People have found that a lot of different kinds of software aimed at a certain direction seems to follow the same pattern. The code seems to follow the same pattern. So it's kind of a roadmap of how one might build software. And so I'm going to present basically design patterns for parallel programming. I'm going to use my own package here, ParTools, which also I now have a partner in that, Clark Fitzgerald, who's a PhD student at UC Davis, working under Duncan Temple Lang. And so I'll use that as an example, but it's not unique, and the things that I'm going to be talking about, you can apply using other packages or your own software. Again, dissent is encouraged, so if you disagree, there's going to be plenty of time at the end for questions. I think I'm probably going to talk for about half an hour, 35 minutes, and so there's plenty of time for questions or comments if you have them. So basically, why are we all here? I mean, actually, many years ago, there was a vice presidential candidate that started the debate. He said, "Why am I here?" And people were asking the same thing. Why are we here? Good question. And I'm going to get to a slide later where I might even dissuade you from using parallel processing in some cases. Certainly, we have the parallel hardware. This is remarkable. This is just highly remarkable. It's my understanding, for example, that probably about 10 to 15 years ago, and this sounds weird today, but about, say 10 to 15 years ago, Intel actually gave up on multi-core. They just decided it was not the way to go. And of course, you know what happened. Now everybody has multi-core. Even in their cell phones, they've got multi-core. So we've got the hardware, 4 cores standard. You can get 16 cores in a pretty inexpensive way. And with hyper-threading, it acts like 32 in some ways. There are GPUs now. Now, GPUs are very specialized, and they're certainly not a panacea, but they're nice for certain applications. And You get many, many cores there. There's the Intel Xeon Phi. There was a very nice talk on that earlier today. And it's amazing. You get 60 cores there, roughly, at the cheapest one. I don't actually own one. I've never bought one, but I'm told that you're talking about the cheapest one is a few $100s. It's a coprocessor. You plug it in, but you're getting a lot of cores. So we have the hardware. And then, we've got what we think is the need for parallel computation. We have big data, and if you subscribe to Google Alerts and have big data as one of your alerts, which I do. I don't know why, because I never look at it, but I feel like I have to. So big data, you need parallel computation, right? Well, we think so, and maybe so. I don't even know what big data is, so it's a little hard to really say. But that's what people think. And this slide is about what people think they ought to be able to do. They believe that they've got the hardware. They believe they have the need. And then they want to say, how am I going to do this? And with R, this comes up all the time. Any of you that are really, really into R, and then maybe you're an R evangelist like Joe Rickard is. That was his title, I think, at some point. People come to you all the time saying, how can I use, I have 4 cores on my machine, how can I use ARM? And sort of the answer is, maybe not so much, okay? But that's what they want. It's not so simple. Now, by the way, I know some of you are really, really expert at parallel computation. Some of you know nothing about it. I'm going to try to explain concepts aimed at the second group. I ask the first group to be patient. What does it mean to be embarrassingly parallel? Embarrassing is good, believe it or not. The term means that there's no challenge. If you're a programmer, an embarrassingly parallel problem is one that it's very easy to parallelize your code. And so it's embarrassing. You're just nothing to be proud of. But for most users, embarrassing is really a good thing because it is easy to parallelize, and you can get some pretty good performance out of it. But there are a lot of overhead issues. And this is really the problem, contention for memory. So, if you have a 4-core machine, that sounds nice. But you have basically one entity, which is memory. And if you have all 4 cores trying to reach that memory at the same time, they can't all do it at once. Some of them have to wait. That slows things down. That really saps the speed. Same thing for bandwidth. How many bits per second can you transfer from the CPU to memory, from the CPU to the network, from the CPU to a GPU? That's a severe limitation. And it's just like how many lanes you have on a freeway. Okay, the more lanes, the more cars per second you can get through at a given speed. And there is a limitation there. Cache coherency, it simply means that if you have many CPUs or many cores, they all have their own cache, probably. And those caches can get inconsistent, and you've got to deal with that. That slows things down. Contention for I/O ports. Limits on the number of network connections. All of these are problems, and that's why the title of the slide is not so simple. Serialization, if you're going to use something like the parallel package in R, the first part, which is from the old SNO, which is meant for a cluster, then the cluster is on the network, probably. It could be multi-core, but you're on the network, and if you have a big R object, you have to serialize it so that it's regular data that's easily transported. That takes time to serialize and then unserialize on the other end. So there's a wish list. What would we like to have? We'd like to be able to run on various types of hardware from R. Okay, we don't want to mess with C++ or something like that. There's a very nice interface. I mean, a lot of you know about RCPP. It's great. But you have to learn some C++ to use it, and then even if you know C++, issues come up, stuff happens. So we'd like to stay with R if we can. Ease of use. Again, what's the typical R user? R is very remarkable from a computer science point of view. From somebody like me, it's remarkable that you have, I don't know how many people we have here, but we have so many non-programmers here who are actually programmers. People who may never have taken a programming class, but have gotten pretty good at using R. And, pretty good programmers. A lot of you, I have to congratulate you. A lot of you, if you didn't come up from the programming world, I have to say, and I'm not just saying this to flatter you, hey, I can't even see you. How am I going to flatter you? Okay? But it's true. A lot of you are better programmers than my students. I'm not kidding. Good for you. Nevertheless, as I said, stuff happens. Cache effects happen, for example. So if you're not one of the cognoscenti, then we'd like to be able to make software that you can use without getting too sophisticated. Now, I said we'd like. For the expert people or the more daring people, we'd like parameters to tweak. Oh, it's not going so fast. Well, maybe I can change this and see if it goes faster. The non-cognoscenti can become daring. And again, that's what's remarkable about R. You see so many people, suddenly they are talking about caches. They never heard of a cache before. This quote, I could not resist putting in here. I won't say who it was who said this, but somebody very famous in the R community. And he said, so it's a male. I've narrowed it down. Help, I'm in over my head here. That's what he said when he started doing parallel code. And I pictured, this, okay? It's not easy. Casual users, even if they're good programmers, again, they learn quickly. Parallel computation is not an easy operation, not casual. Hopefully you're emboldened to learn the subtleties. There are subtleties. The subtleties matter. Sorry, the old saying, no pain, no gain. And if you're going to do parallel computation, you're going to have to do some work. You're going to have to do some digging on R, on the web, I meant to say. You're going to have to learn, you're going to have to learn things that you didn't know before if you want to be good at this. Let's take this is the hello world of parallel computation, matrix vector computation, multiplication. So I want to multiply A times X. A is a vector, A is matrix, X is vector. Result is D. The naive approach, we could parallelize a loop. Here's a loop, a natural loop. We just break it down by rows. That gives us a for loop. I'm sure some of you are users of the for each package, which is meant for for loops. And, well, we have a for loop. So you think you're in business, and you won't be. And the reason is, it says here, the scatter-gather overhead is too big. What does that mean? So basically, if you're using the parallel package, for example, you have a manager node, you have a lot of worker nodes. The manager sends out these rows to the workers. Each one takes its row and multiplies times the given vector x and gets a number, and the numbers are collected back by the manager node. And then, we're in the French-speaking city. Voila, you've got your D, right? Well, that's going to be really, really slow. You're going to be really disappointed if you do that. Okay? Because there's so much overhead. Multiplying one row of a matrix takes no time, but then you have to put it on the network if you're on a cluster. And the net result is you're going to be slower than doing it in serial. The solution should be obvious, that you break the matrix A into rows, chunks of rows, not just single rows, but chunks of rows, and that way you can amortize the overhead. So fine, it's an obvious solution. But casual users may not see this. Just again, put yourself in their shoes if you've already done a lot of parallel computation. just think about their reasoning. They have a for loop. You can see at the top of the slide, still there. They've got a for loop, and they've got a package that says for each. It ought to work, right? If it works, it gives them the right answers, but it won't give it, it'll be a slow answer. And worse, automatic parallelization would miss it. Now, I think several talks I've been to already today have talked about automatic parallel computation in R. And let me tell you, I think that's something we're not going to get. We're going to get it in certain contexts, yes, but I don't think so. And automatic parallelization in this context would miss the fact that you should not do single rows here. Okay, now I'm going to talk about use cases here. So a few examples of just so we know what we're talking about, we have concrete examples of what we might do with parallel computation. And I'm saying they kind of span the space. They don't really, but enough. So let's say quantile regression. Now that's a very computational intensive kind of thing. They use linear programming, if you know what that is. It's iterative. This is pretty complicated stuff, and therefore on a big data set, it is slow. So that's something we might want to parallelize. Nearest neighbor regression, again, you're doing a lot of computation there. We might want to parallelize it. Okay. Graph algorithms, they're really hot these days. Typically you've got thousands of nodes, maybe millions of nodes. All the users of RStudio, let's say, and the ones that they know each other and they're all connected to Hadley or whatever, and you want to do analysis on that. Let's say you want to find communities, that's what they call it, communities within graphs. You want to find groups of people just by software. And that's actually a huge computationally intensive kind of thing. We have run-of-the-mill aggregation. Find just group by whatever, group by political party, and then find the means of something within each group. Very straightforward. Then you have tougher aggregation, credit card fraud detection, for example. There's just so many things you might be doing there. You might want to compare several different people with similar patterns, and maybe it's just one crook that's masquerading as those different people. Now you're really talking about, yes, it's still aggregation, but it's very, very tough aggregation to parallelize. So let's take these as sort of our examples. Now there's a term that I coined called software alchemy. Actually, many different researchers have developed this. This is a reference to my JSS paper last year, and there's a bibliography there of many different researchers who've worked on this. It's really, really simple. In fact, there's nothing complicated in this talk. So you break data into chunks, and let's say you want to do a linear regression using LM. You've got a very large data set. So it's just very simple. You break the data into chunks, chunks of rows of the data. You then apply LM to each chunk. That gives you a beta hat vector, right? And then you just average all of those beta hat vectors. Obviously, you're doing that in parallel. If you have 16 nodes or 1,600 nodes, whatever, they're all working on their own chunk in parallel, and then you average together the results. You get the same statistical accuracy. I make a big deal out of this. Hope I don't fall off the stage here. Last October, really somebody did. I was at a conference, and it wasn't even her fault. And then some guy came up to fix the whatever it was, and she stepped back and she just dropped off the back of the stage. So that's why I'm standing at the front. She was fine, by the way. She landed on her feet. I don't know how. A lot of people are resistant to this, the software alchemy. They say, you're not getting the same answer. You're getting a very close answer. It's, like 4 digits of accuracy, decimal digits. It's just as good an answer because you're getting the same standard errors. Now, again, I'm talking to a mixed group here. This is not a group of statisticians. A lot of people are statisticians, many are not. But you're getting the same statistical accuracy. It's just as good. There's no benefit to either having the original answer that takes a long time or using software alchemy to get another answer, which is just as good in a short time. Okay, and that's going to play a big role here. Not only that, which is interesting, in the computer science area, there's something called superlinear speedup. Let's say you have, just go back to the Intel Xeon Phi, you've got 60 cores. Now, in most problems, if you have 60 cores, you're lucky if you're going to get 6 times speed up, not 60. But, wouldn't that be wonderful if you could get more than 60 times speed up? That's called superlinear. Usually it means a little bit more. But actually with this, the way things are, if you have sort of a complicated algorithm, you actually can get a lot more than R speed up for R chunks. So that's another advantage to it. Useful in some applications. We'll come back to that. And again, it's part of the ParTools package. But you heard me describe it. There's nothing special about it. You can do it on your own. There are worldviews. I have to talk about this just a little bit. This is a computer science term. It means, it means when you have a programming language, how does it view the data, for example? And if you have used the R parallel package, or even the front end like for each, what does it mean? It means you have some sort of manager, and it parcels out data to these workers, and they work on it, they give an answer, and they send it back to the manager. So this is called message passing. Their messages being passed from the manager to the workers. I'm going to refer to it as distributed computing. So as I said, the R parallel package, the part that came from Snow, RMPI, so there's a very, very famous package called MPI. I might as well show you the logo, which people normally program in C or C++. RMPI is a very nice R interface to MPI. I have to warn you, it's a little bit difficult to configure, but it's really quite useful. So again, you could stay in R. That's key. You don't want to go to C++ if you can avoid it. Okay. All right. And then the other major worldview is shared memory. So if you go back to you think about your quad-core PC that you have at home or on your laps right now, then they're all sharing the same memory. So it's called shared memory. And the point is that if I have two different processes, one working on one chunk of the data, another working on another chunk of the data, they can both get to the data. They don't have to send it to each other like in message passing, because it's right there in memory that they both have access to. Personally, I'm of the philosophy that shared memory is the clearer way to program. However, I'm going to, I think the next slide I'm going to say probably you shouldn't use it for other reasons. I have a package called RDSM that does do shared memory worldview in R. If you ever you might hear somebody say that R does not have threads. It doesn't allow each core to work on its own chunk of the process. But in RDSM you can. It's kind of quasi-threads. And then this other guy, without knowing about what I did, he started his own, which he calls thread. And it seems promising to me. If you do go to the C and C++ level, there's a very famous, almost ubiquitous library that you can call to use threads called OpenMP. And if you use GPU, there's CUDA. GPU is kind of a shared memory thing also, although much more restrictive than the regular one. All right, now here's where we really get into the good stuff, in my opinion. What are we really going to talk about here? So I was very pleased to see both yesterday and today in the talks I've been to, many of them used the word hype. That is the most important word when you're talking about parallel computation. There is indeed a lot of hype. And again, not for the casual user. You've got to know what you're doing, though you can learn to know what you're doing. Automatic parallelization, again, nice idea. You can get to it to some extent. And what I mean is no user intervention, no sophistication needed. It's just generally not possible. Should not be expected. And in fact, please don't ask. Okay. People will ask, and I'm sorry, maybe I'm a pessimist, but I just don't see it in the cards. For certain things, yes. Transparency. Okay, so in the U.S., this is really a big deal. In the U.S., in politics, we're always talking about transparency. People want to know what's going on in their government. Everything's behind closed doors. Well, actually, it's really important for software also. What do I mean by that? What I mean is that you've got an API. What is an API? What is it anyway? I don't remember what it stands for. But it's a function call. You have the arguments that you can use to call a function in a library. Must be interface. Programming. Oh, thank you. I knew, out of so many people, somebody's got to know. Application programming interface. It's just a fancy word for saying what are the arguments you use for a function in a library. And you really don't want to be satisfied with that. You want to know what the function is doing. Okay, so that should be a big criterion to be using. Okay. useRs, pardon the pun. I mean, we all are kind of weary of letter R puns in the R world, but let's call them useRs. Why not? We useRs are different from the typical Spark user. The typical Spark user wants to do aggregation. And yes, we do aggregation too, but it's only part of what we do. We want to do, we have iterative algorithms. We want to calculate standard errors. We want to do things like linear algebra, okay? And Spark is just not built for that, which goes back to the first bullet on this slide. There's a lot of hype. Newer technology, machine learning. Now, to me, machine learning is just regression analysis, but fine, well, let's call it that. It was in the subtitle of my book that I advertised to you, so why not? My last book, I don't like the term data science, but I used it in the title for that too. Random graphs I talked about. And so Spark isn't good for any of these, okay, except for the first of those 3 bullets. Okay. Okay, and then, we have the problem. Spark users, if you want to get a job in Spark, let's say in the Bay Area, you better be really, really, really good at all those overhead things that I talked about before, how the network works, the caches and stuff like that. You cannot be a casual programmer with Spark. But with R you can. That was my point a few minutes ago. Software alchemy, as I said, break things into chunk, apply the estimator LM or whatever to each chunk, average all the results. That should be fine in most kinds of statistical computation. Time series being an exception, but most things. And that automatically parallelizes. I just told you can't do automatic, but that in a sense is automatic. Graph algorithms and things like that, the fraud detection, let's face it, those are really, really hard problems. And you probably need shared memory there. Okay, and I was saying a minute ago, I love shared memory, but I'm going to have you stay away from it. But there are some things where you really need it. The idea of state here, what does the word state here mean? It means that if you're going to find the shortest path between 2 people in a Facebook graph, how many hops, right? Or if you go to LinkedIn, that's a better example. If you go to LinkedIn and I plug in, Macron, the new president of France, or Macron, whatever. Thank you. Shouldn't have used that example. If you plug in his name, lo and behold, if I do that, you know what? I'll bet you I'm no more than 5 links away from him, which sounds preposterous, but it's probably true. Of course, I'm well connected, right? But, most of you will find that it's remarkably short. What if you want to find shortest paths like that? in a huge, huge graph. As I said, it's very computationally intensive. And you need a state. You need a state meaning which paths have we tried so far. And so you need to have that collectively available to all of the different workers here. And that kind of dictates shared memory. But I think in most use cases, distributed worldview is fine. In other words, something like the parallel package. Even in large scale, probably almost mandatory. Now, that's what I'm getting into for the rest of the talk. So the bottom line, here is the design patterns I promised. Use essay for the computational stuff, software alchemy, and if you're doing aggregation, use distributed computation. And then you can use essay and distributed computation. Especially this point I'm going to make about leave it there. Now, this is going to be the simplest thing you've ever heard of at a useR conference. It is really simple, but it's very powerful, so bear with me. Leave it there. I'm coming to that. So what about Spark? Among other things, somebody told me that I didn't have enough color in my slides, so I had to have the Spark logo there. Now you have your color. I think that's the last one. Sorry. I can always go back to the screen picture if you like. And this is really hyped. For many years, well, many on computer science scale, for 5 or 6 years, everybody was saying, Hadoop, 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 Hadoop. That it's so wonderful. And a few of us were saying, you know what? There are real problems with Hadoop. And it's probably going to be slow for most users. And then, suddenly, lo and behold, after 5 years, you started to see, there was an article in the computer industry press saying, the honeymoon is over for Hadoop. Okay? And the new spouse is now Spark. And, Spark is definitely better than Hadoop. But you know what? I really am a big Spark skeptic as well, especially for useRs. It's good for certain things, but I think it really gets in the way, both in terms of performance and programming for other things. It's just not useful for a lot of things. And boy, the transparency requirement, sorry, there's probably at least one person here representing Spark. Forgive me. There's zero transparency in Spark. It's awful. And even I am a sophisticated user, at least I think I am. I have no idea. I look at the documentation. I have no idea what it's saying. I have no idea what's going on beneath. And what's going on beneath really matters. Okay? Because, all of the overhead issues and stuff like that. Otherwise, it's going to be slow. So I'm not big on Spark. And I'm so negative about Spark, I have to give a couple of examples here. There have been studies. So I think there's like 12 or 13 authors on this study. I just gave the first one. I think they're all at Berkeley, which is the birthplace of Spark, ironically. But they wanted to do things like non-negative matrix factorization and SVD in Spark. And they knew it wasn't going to work well, but they gave it a good try. They really optimized things to the hilt. And it was, of course, the answer was Spark was really, really, really slow in a lot of cases. And it's just not what Spark was designed for. It was designed for certain things, okay? Now, I wanted to make a big deal out of this side comment here. Sitting at another talk this afternoon, I suddenly realized I've really got to emphasize this so-called side comment here. You guys really have to think about what you want to do with parallel computation. Okay, fine. You've got a data with 10 million rows. Okay, fine. 10 million rows and, 200 variables, let's say, 200 columns. And you say, hey, of course I want to do PCA on this. Are you sure? Because the round-off error in that huge a matrix is going to kill you. You really have to question what you're getting from that. The old thing, GIGO, GIGO, garbage in, garbage out. What are you getting out of all that? is there any meaning at all to those principal components that you get out, even the first one? I have not looked into it, but I have a feeling it's very deceptive. And, I actually argued with this with another guy who's prominent in R. I won't mention his name either. But, where he was at the time, he was working in a lot of sparse matrices. I think it was marketing data, I don't remember, but they're all sparse matrices. Oh, we don't have round-off error because it's sparse matrices. I said, yes, you do. Because if you keep, if you look straight PCA, I don't want to get too technical, but you look straight PCA and you take A transpose A, whatever, and you make a symmetric matrix, and then you, to get the first eigenvector, you have to keep taking powers. And after a few powers, it's not a sparse matrix anymore. So you're going to get plenty of round-off error. So I think you really have to think about whether you even want parallel computation in all cases. Or, versus, maybe you should do a subsample. And that reduces the size of the problem. Maybe you don't need parallel computation anymore. And you're probably going to get an answer that is just as useful to you, maybe more so because less round-off. The other study, these guys did a number of things, machine learning, and I think their abstract is pretty important here. They said, oh yeah, MPI, just non-Spark was much faster than Spark. But, they had to say something nice, and so they said, well, Spark has good fault tolerance. In fact, Spark has great fault tolerance. But do you need it? Maybe not. I think the vast majority of useRs don't need that. And you can actually go to studies on Google Research where they've done, they've got, I don't know, zillions of computers that they use for their searches, right? You go to google.com and your search is handed off to some other machine and it does the work. Okay, they've got zillions of them. So they worry about fault tolerance, to some degree at least, and basically, if you look at their research, they say, it's not an issue. If it's not an issue for Google, it's probably not an issue for you. Maybe. All right, leave it there. What do I mean? It's just so simple. This is embarrassing because it really is simple, but it's powerful. So let's go back to what I said before. Here's the typical thing when you're using the parallel package in R. You have the manager node does a scatter, meaning it breaks the data into chunks, and then farms out those chunks to the various worker nodes. Each worker node does its thing, returns its results to the manager. The manager somehow cobbles together a result, an overall result out of that. That's part C. And the big deal about leave it there is don't do that. Do steps A and B and avoid step C like the plague. Okay, only do step C when you really need it. And I'm going to give you an example in the next slide. But this is really, it's so simple. As I said, it's embarrassingly simple. Just don't do step C. Have the workers do their computation, they get their results, and let them keep the results. Don't have them send it back to you. Okay, so here's an example. Let's say we have a data set. When you're working on data, typically you've got many dozens and dozens of things that you do with the data. Let's say you do 4 things with the data in this case. So you have some categorical data, categorical variables. And so you want to change those to dummy variables. Let's just say you do. I mean, you may or may not. Then you've got some NA values. And let's say you're just going to replace your NA values by means. Don't do that. It's a stupid way to handle missing data. But let's just say you're going to do that. Okay? Some people do it. And then you're going to remove some outliers just with the 3 sigma rule. Again, maybe not a very good way to deal with outliers, but just as an example. And then finally, after all these operations, you're going to do some sort of linear regression. Okay? So the idea is, before I go to the slide that shows you the code, except for the last bullet, the first 3 bullets, you don't need the workers to return their results to you. They're just working on their chunks of data, and they convert the categorical variables to dummies in their chunks of data, and then they replace the NA values in their chunks of data. Just have them do that without reporting back to you. Okay? And then finally, you maybe in the end, you have them report back to you the data set that they've now put together for you, and you do LM. Or maybe you don't even do that. I'm going to get to that in a minute. Let's go to the code. Okay. And that's what it says at the bottom of the slide. You can do that, even the last step in parallel if you use software alchemy SA. All right. I give you the next slide with some trepidation because I'm going to compare some packages. It's guaranteed to offend some people. I know you're going to say I'm totally wrong, and of course you're absolutely right. Well, you want to see it? Here goes. A reprieve. Okay, so I just have 3 packages here. I have my own package, ParTools. I have DDR. I didn't even spell it right. It should be capital R. And I have multi-deployer. I can vouch for the first row of the table. I think the second and third rows are correct. They're vague anyway, so I'm okay. But in a sense, as you go down the table, you're getting more and more user-friendly, more high-level operations, but losing flexibility. But all of these basically say leave it there. And in fact, if you go to Hadley's GitHub site on this, on the last one, multiplier, you will see that he says, yes, leave the data there. That's the key idea. Again, very simple but powerful. But what I also do in ParTools, or we do, is have the files distributed as well. Now, by the way, some of you might have been to a talk earlier today. There was a very nice package called Matter, M-A-T-T-E-R. The speaker was, I think she's a grad student at Northeastern. Very, very impressive. And again, it was on distributed files, although with more structure than what we have. But the idea here is that, since you're going to be leaving the data there for many, many steps, why not have the data chunked in files to begin with, okay? And instead of having one monolithic file, why not just have all the data chunked to begin with? And that's what Hadoop and Spark does very, very well. And that's where they get one of the ways they get the fault tolerance, okay? So ParTools does that. Here is just a brief view of what ParTools does. So there's a function you can call name file split. It does what it says. If you have a file whose nominal name is X, and it starts out as a monolithic ordinary file. This function just does what it says. It splits the file into x.001, x.002, and so on. And then from then on, let's talk about x005. So from then on, node 5, worker node 5 is always going to be handling the data from x.005. And so it's nice to actually have that on disk. And then there's a file read. So I want to just say a little bit about this third bullet, file read. So the point is that when, in ParTools, if node 5 reads X, then the innards of file read sense that, this is node 5. So it'll read x.005. But we can use the same code that says read X, okay? And then the same thing, it reads into a variable D, a data table, let's say, frame. And from then on, okay, each node 5 is going to be working on its portion of D. D is going to be a distributed data frame at that point, but it's, node 5 is only working on its portion. So let's say we go back to the previous slide. We want to change some categorical variables to dummies. We want to remove NAs. We want to remove outliers. Let's say, now you've all used the various apply family functions in R. So in order to use apply, we've written these little functions that change NAs to means and so on, okay? So here's some code. I mean, it's not good to put much code on in a talk, but cluster evalq is just a function in the R parallel package. It just says go to each node in the cluster and execute, in this case, XY assigned from apply, okay, with the NA mean. And the point is that in that line, that first line of code, what are we doing? Again, cluster eval Q says this is from the R parallel package, this is not partools, but it's using partools. It's saying to each node 5, for example, node 5, please call apply with the arguments xy2 and NA to mean, and then return the result, assign the result to a variable xy. Your variable xy, node 5, not mine, the manager. Okay? So at that point, xy is also distributed. Node 5 has its chunk and so on, but they all call it xy. And then there's another call to do delete the outliers and so on. And then finally, the last line in this slide, we wanted to do our linear regression, and I'm recommending that you use software alchemy to do that. And so there's a function in partools, CALM, for chunk averaging LM, to do that. But again, you don't have to use partools for this. Okay, so I just explained this. So the key point, is we have data stored in distributed fashion. We leave it there as long as we possibly can. We don't collect. So in DDR, for example, there is a function you can call that says collect. You have your distributed vector, whatever it is, and collect it back into a monolithic vector at the manager node. Basically, what I'm saying here is try to avoid using collect as much as possible, and that way you're not overloading the network, you're not encountering the network overhead, you're doing things in parallel, no network delay, no serialization. Once in a while you might have to do a collect operation, but do it sparingly. Okay, and then once you have your new distributed item, which was, let's see. Once you have your new distributed item, xy, then you can write that to disk also, if you need a persistent version of it. Okay, so there's file state for that. So again, heavy use of software alchemy. In partools, we've got it for LM, we've got it for GLM, we have it for k-nearest neighbors. I wrote random forest here. That's a little bit misleading because the function that does random forest also does SVM, also does neural networks. It basically does almost any kind of classification scheme you want. And not only that, if you want to write your own SA function, you can do it really, really simply. A minute ago on the slide, I had CALM for the software alchemy version of LM. It's like 3 lines. So you can write your own. It's very easy. Okay, but sometimes you have to do collection. And so we have a function in partools is add to lists. I'm beginning to run out of time, and I want to make sure I have time for questions if there are any. But what does it do? It does what it says. You have 2 lists at different nodes, and they both have an A and a B. Maybe one of them also has a C. And you'd like to get a grand list that adds them element by element. So the A equals 3 in one, B equals 5 in the other. You want A to be 8 in this collected one. And so we have that. So conclusions. No silver bullet, sorry. When that Spark salesperson comes around, you're going to have to resist. Sorry, it's just not that simple, okay? Unless you want a lot of grief. But doing what I said should take you a long way. It's not 100%, but software alchemy for the computational stuff. For aggregation, no, don't go to Spark. Just use the leave it there principle, and use distributed files, distributed objects in the way I showed. And again, it doesn't have to be partools. You can do this in other packages. I mentioned a couple. You can do it on your own. It's just a principle. It's a design pattern, as I said. Okay. And by the way, even for partools, we use the R parallel package as the base, and we're thinking of using RMPI as the base, just because it probably would scale better. But, you know, it's just a principle, really. Thank you. I'm ready for dissent. Do we have a microphone?
So I'm bothered by one thing in your LM example. If you, unless you do random chunks, it's awfully easy to get situations where the thing is singular in every chunk, but you've got perfect estimation. Well, not perfect, but the standard good estimation in the aggregate.
Right. You know, I don't know if everybody got that, but he's worried about taking chunks. Excuse me. Say we have 10 million rows and we have 4 processors. So take the first 2.5 million rows for the first processor or first core, whatever, and the next 2.5 million rows for the second core and so on. And he was worried about the ordering because, and this is true, this really came up a lot when I submitted a paper on this. And of course, it's perfectly correct. In a lot of data, you do have to do a random shuffle of the data first. And so, for example, the function file split that I mentioned, to split a big file into small ones, it has an option to randomize the chunks. And then there's another function, distributed split, to take a single data frame and make it distributed as well, and it also has an option like that. So definitely true. Okay. There's a guy back there. Sorry, I can't see you, but I know you're there.
Okay, it's not clear to me how your part tools differs from Bill Cleveland's divide and recombine. And Bill's tools scale from in-memory to disk to Hadoop. That's one question. The divide and, there are a series of packages. His website is Delta Row now, and the Hadoop package is Replay. The other thing is, I think the Spark people would differ from your assessment for machine learning. In particular, using stochastic gradient descent and algorithms, I think it's not restricted to just the type of breaking it into groups and aggregation.
Well, before you give him back the mic, please. I didn't hear what you were talking about. You said somebody.
On
his website. Who's he?
Oh, Bill Cleveland.
Oh, okay.
His divide and recombine.
Right. Well, actually, you know, that he's one of the... Okay. All right.
He's been doing that a while, and it looks similar to Part Tools.
Absolutely.
And it scales to Hadoop from memory to disk to Hadoop.
Right. So actually, he and his group, they have a package. I don't remember what it's called, but it's the same idea as software alchemy. Okay, it's not the same as Part Tools because that's a different issue. As far as I know, they don't do distributed files. Software alchemy was only part of what I was saying. Okay, but absolutely, and again, as I said, if you look, if you go to my paper on the Journal of Statistical Software last year, you'll see, I think, a fairly complete bibliography of various people who have developed this idea of software alchemy. And Bill Cleveland didn't invent it. I didn't invent it. Actually, the first reference I can ever see is somebody in Taiwan, but probably people were doing it long before that. We just formalized it and showed that it worked and stuff like that. As far as Hadoop goes, you know, I don't know if I should tell tales out of school here, but hey, why not? So here's the deal. So, you know, I'm one of the organizers of the Bay Area R-User group, you know, in Northern California. And, you know, we had a guy, this is going to be anonymous, but some people will figure out who I mean. But anyway, he gave a great talk on Spark R. And I asked him, well, how fast is that relative to, you know, just doing something else without Spark? And he said, well, we don't know. We haven't tried it on, all we know is how well it does relative to Spark and Python. And then about 20 minutes later in his talk, somebody else asked a similar question, and he evaded that. You know, I'm sorry to put it that way, but they're really they're big overhead issues. with Hadoop and Spark. You know, you do a shuffle whether you need it or not. You have, in Hadoop, worse than Spark, you have a lot of disk writes, and there are just some fundamental problems there. So I think we have to disagree on that one.
Yeah, I think that Spark mainly doesn't really do Hadoop or MapReduce. What it does is it sometimes, if it's not done in memory, uses HDFS, the distributed file system, which is the main thing that it does. In terms of transparency of Spark, they actually do have a page on their website, several pages that describe the algorithms for machine learning and how they parallelize them and why it is fast. And at the Spark Summit, I did see talks on speed comparisons that were quite good. But there's one issue that I think the people here have to start thinking about, and that is streaming data. And that's going to become more and more common with sensors and not just Twitter, but many, many cases in medicine, environmental studies. And Spark now has essentially reduced the latency to 0, but there's Flink, which is a European initiative for streaming data, and there are other systems, but Spark and Flink, I think, are among the leaders for streaming data, and I think that statisticians have to start thinking about this type of data analysis, or they're going to be left behind.
Yeah, no, I think that's a very good point on streaming. In fact, when I gave a talk on this at another place, somebody tried to defend Hadoop by saying that they're interested in throughput rather than latency, although you mentioned latency. But yeah, I think streaming is really a big thing. Anybody else?
Hello, my name is Alok, and my question is like kind of extension of what the previous gentleman mentioned. So I'm not sure if you are aware about Apache SystemML. That actually allow you to write the code in a R-like syntax, and it kind of solves many of the problems you discussed because it has this dynamic optimizer for every iteration. It computes whether you want to shuffle or how you want to partly do it in local or distributed. So I was wondering, when you did your analysis with respect to Spark, did you include SystemML? Because when we do some of our, okay, I'm from IBM, and it's a SystemML is IBM product also. It's open source. So we had some very positive results, especially when this kind of problem you mentioned. So I was wondering what's your thoughts on.
Right. Well, no, I certainly agree that Spark people have really done a wonderful job of trying to optimize. It's just a question of whether the basic model is right for useRs, and for the reasons I gave, you know, I'm very skeptical of that. You know, the other thing is, you know, back to the transparency the previous guy was asking about. I'm talking about transparency at the lower level, the basic Spark APIs. I'm not talking about transparency as to how they do random forests or something.
I think my question was more on Apache SystemML that actually takes R-like code and do a dynamic compilation and generates a DAG of Spark jobs. So that pretty much solves many of the problems you mentioned. So my question was that when you did this evaluation, did you consider SystemML, it's open source product, whether it solves the pain points you pointed in Spark? Does it solve for you?
Okay, well, I'm not sure I totally followed what you said. I think I followed enough. Again, forgive me, but I think I have to be very skeptical of that. You know, I've heard this so many times that we optimize this and that, and there are just so many things. You can't optimize everything. I'm sorry. Yeah, there you are. You can't optimize everything. It's just like people, you know, talk about SVM. The people who really, really love SVM say, well, or was it SVM? You know, yeah, probably. They said, oh, well, we found the optimal partition. But it's optimal for the setting that they created. Doesn't mean it's optimal for what you want to do. And, you know, please send me email and I'll look at whatever you'd like. I'm very curious, but I'm a little skeptical.
So we have time for one more question.
Yeah. It's Wimbledon now, so we need the people, the kids to be running across the court like that with the mic.
Hi. I was wondering if
Where are you?
I'm here.
Oh, I don't know where you are.
Oh,
there, okay. All right.
So I was wondering if you have any advice for package developers, how people can include parallelization within their package without making it hard for the users.
You know, for packages, if it's something like quantile regression or something that's very computational, you can probably just add an extra argument, for a cluster and say, do you want to run this on a cluster? And that would probably work pretty well. Again, you'd have to write a short function like I have for CALM, very, very short, 3 or 4 lines. So for that kind of thing, fine. If you're talking about fraud detection, I don't know if you're going to write a fraud detection package, more power to you, but I can't help you. Okay. All right, sure.
Loved the comment about the need for some systems level skills to
Right,
use
sure.
these tools, right?
Yeah.
And I think we all sort of deserve a pat on the shoulder how we got to where we are in terms of basic programming skills. But I'm with you. The system stuff's lacking. So,
Right.
can you foresee any chance for getting everybody sort of to the next level with that? Just how software carpentry made everybody who didn't program yet at least a moderate programmer?
Right. Oh, that's really such a good question. His question was, well, how do people learn those system skills? The cache stuff and stuff like that. It's really, really hard. You can go to my book, my old book, the Parallel Computation. I have an overview there, but it's still not enough. I'll tell you, I'll share something with you here. I've already praised people here for being such good programmers, even though they came from nothing, no coursework. The next time you talk to a computer science graduate, somebody who has a computer science degree, even somebody that's really sharp, ask them the following simple question. How does an operating system boot up? My PC is down, I push the button, it does various things. What does it do? I would say 95% of them would not be able to answer that really simple question. So the point is that even the computer science graduates don't have a good systems knowledge typically. The ones that do, here's how to identify the ones that do, and some of you are employers. Somebody comes in and they're wearing a backwards baseball cap and they look a little weird. They probably can answer that question.
Thank you, Norman.